Alright, we're back at our vectors section on vectors and the dot product, and now we're going to look about how to break a vector down into two orthogonal vectors. Remember, orthogonal means they're perpendicular to one another, and we do that in a process that's called decomposition of the vector. And to do this, we use an idea of what we call a vector projection. Now, I hope that this is going to make sense. I'm going to try to explain it step by step here before I actually do an example of it. So let's consider two vectors, and I have two different drawings here. Vector V and vector W that are drawn tail to tail, which means the initial point to the initial point at point A. So on this first diagram, here's vector V, and all this is vector W, including the part that's covered up in green. On this vector, or this diagram, here's vector V, but vector W goes out in this direction. So as you can see here, I have to extend in the opposite direction for this projection. The projection is going to be the part that's in green. Notice that it's either in the same direction as W, which means parallel, or it's in the opposite direction as vector W, which also means that it's parallel. And also look at the two vectors here. The projection being called vector V sub 1, and this other vector in blue being vector V sub 2. See how they are perpendicular, or at least they're supposed to be drawn that looks perpendicular to one another. To find the decomposition of vector V of these two orthogonal vectors V sub 1 and V sub 2, we state that V sub 1 is the projection with respect to vector W of vector V, and that V sub 2, that's the one in blue, is going to be orthogonal to W, and the sum of the two vectors that we're trying to decompose this into is equal to the actual vector that we're dealing with, vector V, again in the black here. Okay? Now a couple things to keep track of. Vector V sub 1 and W are parallel. For some scalar C, V sub 1, vector V sub 1 is equal to C times vector W. As I mentioned before, here with this way it's set up here with this acute angle this way, it's in the same direction, and here with the acute angle in this direction, notice the dotted line that goes out from vector W, okay, it's in its opposite direction here in green. So that's considered parallel. Second, the second vector, V sub 2, that's drawn in the blue here, are orthogonal to vector W, which means, of course, that V sub 2 dot product, that's dot product vector W, is equal to 0. Perpendicular or orthogonal means 0. So now, let's go over here. We're going to start with this guy right here. Vector V, and in both cases you can see this using the consecutive method, that vector V is equal to vector V sub 1 plus V sub 2. That vector V is equal to V sub 1 plus V sub 2 during the tip to tail or the consecutive method. Okay, I am going to take the dot product of V dot W. Now remember, we just said that 2 seconds ago that V dot W here, okay, that vector V is determined to be the sum of the two vectors. So what we have V dot W, we have the sum of the two vectors dot vector V here. This is the dot product. I just said V, but I meant to say vector W. Excuse me. Doesn't help when I say I'm wrong. Now, one of the properties of dot products was that we were able to multiply, dot product multiply, like the distributive property, over the sum of the vectors. So this sum of vectors, dot product vector W, is the first vector, V sub 1, dot W, vector W, and vector V sub 2, dot vector W. There's sum. Remember, these are numbers. Now, it just gets funner and funner here, okay? Vector V1 and vector W back here are parallel. So that means vector V1 can be written as C times vector W for some value C. So I replace V sub 1 with C times vector W. Also notice back here, vector V sub 2 dot vector W is equal to 0. Actually, I wrote down the 0 vector, I guess because I'm talking about adding the vectors and stuff like that, but it would actually be just the number 0 here. And of course, that means here, when you have the same vector dot product, we had this also as one of the properties, that this was equal to the constant times the magnitude of that vector squared. All right, now we have this is equal to this. Let me bring it on down. Alright, so now what I'm going to do is I'm going to divide both sides and solve for C. I'm going to divide both sides by this. This is non-zero, positive number here. That gives me this. Okay, now, remember that V sub 1 is a projection of the vector V. That's how we described it with onto vector W of our key vector here, vector V. So, what I'm going to do is I'm going to write V sub 1 as this multiple times W, because that's what we have right here. That it's a scalar multiple, because they're in the same direction or they're in opposite directions. I'm going to replace C with this expression right here. And this gives me the following definition, what we use to for the decomposition of a vector into orthogonal vectors. If vector V and vector W are two non-zero vectors, then the vector projection of vector V onto W is given by this. That's the notation. That's the vector projection of vector V onto vector W, and it's equal to this expression right here. Vector V dot vector W all over the magnitude squared times vector W. Now to break it down, and these are the steps that we're going to use, to decompose vector V into vectors V sub 1 and V sub 2 parallel to W and orthogonal to W, this one is parallel, this one is orthogonal, respectively. Then we have that V sub 1 is equal to this projection, and that V sub 2 can be found by taking the difference here of vector V and vector V sub 1. So let's see if we can apply this. So it's kind of like we're taking this vector and we're breaking it down into two perpendicular vectors, like maybe one's north-south, the other one's east-west, to kind of get an idea of the way that this projection is made up of. So, here we go. Find the projection of vector V onto a vector W here. So by definition, this is equal to, here I'll put it down here, is equal to vector V dot vector W all over the magnitude of vector W, magnitude squared, times vector W. So I'm going to substitute in. This is going to be 7, negative 3 dot negative 2, negative 6. That's negative 2, negative 6 up here. All over the magnitude here of W, which is negative 2, negative 6, magnitude squared, times the vector W, which is negative 2, negative 6. I need to simplify this. So up top, that's going to give me 7 times negative 2 plus negative 3 times negative 6. By now you should be able to do that in your head, I would hope. And this is going to be equal to the square root of negative 2 squared plus negative 6 squared, and then all that's squared. So up top, I get negative 14, oh, hang on, I forgot to write one more thing down, times vector W. So this is going to be negative 14 plus 18. This is going to be the square root of 4 plus 36, square root of 40, and that's squared, so that's 40 times negative 2, negative 6, the vector negative 2, negative 6. So up top here, I have 4 over 40, negative 2, negative 6. Of course, that's 1/10. So I get negative 0.2, negative 0.6. All right? That's the projection of vector V onto vector W. Okay? Now, I want to find two vectors, V sub 1 and V sub 2. I'm going to use the second part down here. V sub 1 and V sub 2. This means such that V sub 1 is parallel to W, right? And that V sub 2 is orthogonal to W, vector W, and their sum is equal to V. Alright, so V sub 1, back here, is the projection, negative 0.2, negative 0.6. Alright, so now I'm going to take this vector and I'm going to find vector v sub 2 by doing vector v minus vector 1. So this would be vector v is 7, negative 3, and vector 1, here let's write it as negative 1/5, negative 3/5, if that helps. So vector v sub 2 would be equal to 7 minus a negative 1/5. That'd be the same as 7 plus 1/5. That's 36/5. Negative 3 minus a negative 3/5. That's the same as negative 3 plus 3/5. So that'd be negative 15/5 plus 3/5. Negative 15/5 plus 3/5 would be negative 12/5 or negative 4/5 if I have that written down right. Now there is a way. Did I do that right? Let me try that again. Hang on a second, maybe I didn't do that right. No, I don't think I did that right. Okay, that's negative 15/5 plus 3/5 is negative 12/5, not negative 12/15, negative 12/5. Whew. Gave me a scare there. I didn't think that was going to come out right. And there are the two vectors that are in question. Now if you were to take their dot product, I'm not going to because I'm lazy, but if you were to take their dot product, you should end up with 0 because these two vectors are orthogonal. So this sets us up to try to use this decomposition maybe to do another kind of application problem next video.